So what is architectural solar? When folks think of architectural solar, building integrated photovoltaics is likely the first thing that comes to mind. Building integrated photovoltaics, or BIPV, is when solar forms or is integrated directly into a building component, something that provides function beyond energy production. Since the 1970s, BIPV has been continually promised as the next big breakthrough. During that time, the global solar industry has deployed greater than 1 terawatt of capacity. With the promise of BIPV being right around the corner, building professionals have tended to turn a blind eye to more standard solar technologies that are being deployed at scale. This is understandable, given that solar has a reputation of being an eyesore or an afterthought. The trouble lies in the fact that a large percentage of the 1 terawatt of capacity has been architecturally coordinated in some way. We believe that defining architectural solar as such will invite participation to a broader field of practice than just BIPV. ASA defines architectural solar as solar energy generating technologies that have architectural significance or are coordinated with the architectural design process. The concept of architectural solar represents a broad continuum of integration opportunities. As one progresses across the continuum, the level of integration and architectural coordination increases. On the left side of the continuum, we have site-applied and site-integrated photovoltaics. Central to the continuum, we have building-applied photovoltaics. And then the BIPV subcategories of externally integrated, cladding integrated, and envelope integrated make up the continuum's latter half. On the left side of the continuum, there is a low level of architectural coordination required. The installations are adaptable to standard products and have the potential to be independent of the site's primary construction schedule. Central to the continuum is where a deeper level of interaction with a building occurs. These installations are typically impacted by the construction schedule. There also may be certain applications that require customized products to meet various architectural constraints. BIPV on the right side of the continuum is where standardized products are rarely adaptable to the architectural constraints and customization is likely required. In addition, there tends to be a high level of coordination with multiple trades and construction schedule. The benefit of pushing towards higher levels of integration is that solar technologies have greater opportunity to serve as building components, leveraging costs that would otherwise lack the benefit of energy production. On one end of the spectrum, architectural solar may be a utility scale PV array that is coordinated with a master plan community or a corporate campus. The category we define as site applied because it lacks function beyond energy production, but can require some level of coordination. Through a category we define as site integrated, architectural solar can integrate with architectural programming by applying shade, weather protection, artistic expression, or one of the many ways in which solar can add function beyond energy production. Building applied photovoltaics, solar that lacks multifunctional benefit, can also be considered architectural solar if it is coordinated with new construction or helps accomplish programmatic goals. One step further along the continuum brings us to building integrated photovoltaics. Building integration presents an opportunity to leverage solar technology as a building component, which has the potential to reduce costs by avoiding the need for the material that reside in its place. We define the least integrated of all the BIPV categories as externally integrated. Externally integrated can be thought of as elements that sit outbound of the building's skin or envelope. Elements such as sunshades, awnings, rooftop canopies, or physical barriers. Moving one step closer into the envelope, cladding integrated PV forms an outer element of building skin. And lastly, solar can be envelope integrated by forming a barrier between indoors and the outdoor environment. Architectural solar is inclusive of this entire continuum because the full spectrum of integration opportunities enables the design community to accomplish its programmatic goals with all the possible tools at their disposal. This is important because it's happening today at scale. Architectural solar leverages existing infrastructure. Its distributed nature avoids transmission losses that are estimated to be 5% on average by the U.S. Energy Information Administration. Architectural solar presents opportunities to integrate solar on vast vertical surfaces that can add resiliency to an installation by being less prone to soiling. And today, municipalities throughout the U.S. are adopting aggressive building performance standards that can require on site renewables to meet performance targets. Ultimately, architectural solar is a compelling and achievable design opportunity. It is therefore critical that the architectural community understands the full continuum of integration opportunities that are available to them. In the content to come, we will dig into each of the categories outlined here to gain a deeper understanding of how each category can solve the programmatic needs of the design community.